for a prosperous and sustainable 21st century. My name is Mingzi from A-Star, and I will be your MC for today. The event is organized by the International Peace Foundation as part of its Bridges program and hosted by A-Star. Let's start by welcoming Mr. Uwe Morawetz, Chairman, International Peace Foundation, to say a few words. Mr. Morawetz, please.
Yeah, welcome to the 5th ASEAN event series, Bridges, Dialogues Towards a Culture of Peace. Bridges is facilitated by the International Peace Foundation, a non-political and non-religious foundation under the patronage of 21 Nobel Peace Prize laureates based in Vienna. The events are hosted in cooperation with various local partners, including some of the country's major universities, and I would like to thank A-Star for hosting our event today. Having started in October last year, Bridges will now be continuously held in Singapore until March this year, involving the participation of Nobel Laureates for Peace, Physics, Chemistry, Medicine, and Economics. The 5th ASEAN series of Bridges follows a series of 500 Bridges events, which the International Peace Foundation has already hosted in Thailand, the Philippines, Malaysia, Cambodia, and Vietnam since 2003, as an independent contribution for a decade of culture non-peace, initiated and promoted by the United Nations General Assembly. The pluralistic program of Bridges highlights the International Peace Foundation's intercultural and transdisciplinary approach towards peace. The foundation does not take sides, but acts as a mediator by creating an independent platform for dialogue where representatives of science, culture, politics, economy, religion, the media, and youth can meet, share their viewpoints, listen to each other, and find mutual ways of understanding and cooperation. Therefore, the foundation itself is a bridge and a facilitator between different language groups in our divided societies where politicians speak another language than artists, and business and religious leaders another one than scientists. In a highly interdependent world, problems cannot be solved by either one of these language groups only, but by working together. After the success of Bridges in Thailand, the Philippines, Malaysia, Cambodia, and Vietnam, the International Peace Foundation has been invited by other ASEAN countries to build further bridges towards peace and international understanding by expanding its program in Southeast Asia to stimulate the intellectual, scientific, and cultural exchange in the region. The aim of Bridges is to facilitate and strengthen dialogue and communication between societies in Southeast Asia with their multiple cultures and faiths, as well as with peoples in other parts of the world to promote understanding and trust. The events aim at building bridges with local universities and other institutions in Southeast Asia to establish long-term relationships with Nobel laureates in all fields, which may result in common research programs and other forms of collaboration. By enhancing science, technology, and education as a basis for peace and development, the events may lead to a better understanding of cooperation for the advancement of peace, freedom, and security in the region with the active involvement of the young generation, ASEAN's key to the future. This is why Bridges is not designed as a one-time event, but as a continuing process of synergies to make the series of events a success for Singapore and for Southeast Asia as a whole. I'm grateful to the Singapore Honorary Chairman of Bridges, the Honorable S.R. Nathan, the Singapore Chairman of Bridges, His Excellency Minister Heng Swee Keat, to A-Star, as well as to our other partners and sponsors who have enabled us to make the idea of Bridges a reality. I would like to say thank you to everyone present today for taking part in this program. May it help us to facilitate a new culture of peace through dialogue, transcending its definition as merely the absence of war or armed conflict into a new understanding what the basis for peace is: education. In this spirit, we welcome today the 2010 Nobel Laureate for Chemistry, Professor Ei-ichi Negishi, and his wife, Sumire Negishi, who have kindly agreed to come to Singapore to support the events. We look forward to his keynote speech and to your important contribution to build bridges. Thank you very much.
Thank you, Mr. Morawetz. Now let us welcome A-Star Chairman, Mr. Lim Chuan Po, to give us his welcome remarks. Chairman, please.
Nobel Laureate Professor Ei-ichi Negishi and Sumire Negishi. Very nice to meet you again. Excellency, Ambassador of Japan to Singapore, Takeuchi-san, distinguished guests, ladies and gentlemen, very good afternoon to all of you. Let me join Mr. Morawetz to welcome you to this public lecture by Professor Negishi as part of the 5th ASEAN Bridges event. As you would have heard from Mr. Morawetz, this event is organized by the International Peace Foundation, and A-Star is very honored to be able to host this event, especially given the mission of the event of the International Peace Foundation. I shall not spend too much time introducing the International Peace Foundation because that has been very nicely explained, or introduce Professor Negishi because his CV is well known to all of you. I should just mention to all of you that Professor Negishi is actually very familiar with Singapore. He started visiting Singapore, I think, as I recall from last night's conversation, more than 15 years ago. And in fact, I last met him on 2 separate occasions, I think 2010, 2013. So I look forward to actually seeing more of you in Singapore going forward. I just want to mention that Professor Negishi is really passionate about using science, promoting science, and using that as a way of connecting communities and promoting mutual understanding and respect. And this is something that Singapore and A-Star shares very much. And I shall talk about the A-Star perspective of this issue. So we share this enthusiasm and dedication. Through partnerships with other public sector organizations, A-Star Science and Technology also contribute to the well-being of Singapore, and of course, beyond Singapore to the wider region, whether it's in the healthcare and wellness solutions that we develop, or just conducting science and technology research impacting urban solutions in Singapore that then can be shared with the wider community. These are the kind of things that we worked on that will bring benefits both to Singapore and to the wider region. As the lead research agency in Singapore, A-Star supports Singapore's key economic clusters through the excellent science and innovative technologies that we develop. And of course, very importantly for A-Star, nurturing the next generation of scientists and engineers that will continue this effort. Research is a human enterprise, and I think Professor Negishi will elucidate this very well later on. And therefore, talent is key to science and innovation in A-Star and of course in Singapore, and for that matter, in any research hub in the world. I am proud to say that as an organization, A-Star as an organization of over 5,000 people, we really have a very rich mix of talent. Talent coming from around the world, and of course talent coming from within Singapore. And in fact, over 40% of the researchers in A-Star, they come from over 60 different countries. And many of you are representing different countries over here. All of you bring with you your own scientific networks, diverse backgrounds, and of course, you also bring experiences that broaden the collective experience of everyone in A-Star and in Singapore. Many of you, especially the senior scientists amongst you, you also have been the bridges for A-Star in Singapore to form that kind of connection, that kind of network with the research communities overseas. So you are really bridges already within the A-Star community. Likewise, our young scientists are also building their own bridges. Since 2001, A-Star has supported over 1,300 Singaporeans, students, including our MC here, through scholarships to pursue research training at top universities overseas, and of course locally. They are part of the pool of Singaporean scientific talent we are committed to nurturing and grooming to become our future scientific leaders. Over 400 of these scholars have since returned, and they are now working in A-Star, but not just in A-Star, they are also working in our universities, our Institute of Higher Education, and very importantly, also the industry and the wider public sector. Through their training abroad, they were exposed to the rich milieu of research and innovation environment that is so crucial to the pursuit of excellent science and impactful innovation. You had to be immersed for you to distill that kind of experience. And I think Professor Negishi very carefully highlighted his own experience to me last night. They will then become the chain agent by the time they come back to Singapore within our system. At the same time, they also bring back with them new networks, new collaborations, new perspectives. As they bring a touch of Singapore to the world through their participation in this overseas institution, we also bring the world to Singapore. To complement the scholarships for Singaporeans, we also welcome many international students from all over the world to A-Star and our universities to participate in undergraduate research attachments, PhD training, or postdoctoral training. We started welcoming these students from around the world from 2008, and already over 800 young researchers from more than 50 countries across North and South America, Europe, Asia Pacific have benefited from such research opportunities in Singapore. Many of the students continue to maintain links with us, and we are glad to see that some of them, in fact, have taken up research positions in Singapore within A-Star or the industry. At the same time, others have either returned home or moved on to other research hubs to pursue and to continue their research training. For those who have left us, they bring a part of Singapore with them wherever they go. They, of course, constitute the additional bridges that came to Singapore and then went out to the other parts of the world. So Professor Negishi, last night I said that I will share one story with you because I have to find particular meaningful connection to Purdue. 2 years ago, through this scholarship program, A-Star received our first student from Columbia to do PhD in Singapore. Just in case he's also here, show your hand if you happen to be here. Okay, I don't think he's here today. So let me tell you his story, because he was the first student from Columbia to do PhD in Singapore. We decided to let him be the valedictorian to represent that cohort that year. So he went on stage, spoke English very fluently for a Colombian student, and the story was very interesting. He was one of the top students from his university in Columbia, and then decided to do masters at Purdue University. Yeah. And he went there, spent 2 years, did very well, but more importantly, he discovered a passion for research. So he asked, and rightfully so, to see his supervisor and say, Prof, can you give me some advice? I'm thinking of doing research. And the professor, very sensibly suggested, look for a top lab, look for the person that you want to work with, and if they accept you, but make a few choices. If they accept you, you are off to a good start, and then you take it from there. But this student is not an ordinary student. So he next asked, is there a plan B? And the professor, I think, was just trying to get him out of the office, wasting his time. So he said, go as far as you can. And guess what this student did? He went back home to Columbia, plan A, of course, still in his mind. He took out his globe from primary school, and he looked at Columbia, and then he imagined a line through the center of the earth, flipped it around. It turned out to be Southeast Asia. And of course, Singapore, you can't even see it on the tiny globe, but he saw the name Singapore, went straight to the net, put down there, Singapore PhD. The whole page that came out in the Google return were all about Singapore International Graduate Award, short form SINGA, which is a scholarship that we created. And he sort of said, is this serious? Not one of those funny places you go down there, you end up in forced labor camp. So he clicked through, and then of course the website came up, sensibly contact us, click through, there was a real email that popped up, And then he entered his question. He said, "Oh, I came upon your website. Please advise, how I should proceed." He could not believe himself. About 3-4 hours later, in spite of the time zone difference, there was actually an email reply from our officer, A-Star Graduate Academy officer, and said, "This is what you have to do." So he submitted his CVs and all those things. And one thing led to another. He was shortlisted, interviewed. He came to Singapore. So it's a connection with Purdue because you have a deep connection with Purdue. This is how Singapore is connected to the world and how the world is connected to Singapore. So this rich mix of scientific talent contributes to this very vibrant research community over here. But the bridges that we have built through Singaporeans being exposed overseas, or our international friends, having experienced Singapore, are really what deeply connects Singapore to the wider international community. It is therefore my hope that today's program and other Bridges event will inspire more people and demonstrate how crucial science and technology is, not only to improving lives, but fostering much better mutual understanding and, very importantly, respect across the different communities. I think the world needs a lot more of this mutual understanding and respect. This is what humanity absolutely needs if we want to succeed together in tackling the global challenges confronting us today. So with that, I hope that all of you will have a very meaningful talk, and I look forward to the insights from Professor Negishi. Thank you very much.
Thank you, Chairman. It is now my pleasure to invite Professor Negishi to deliver his lecture. Professor Ei-ichi Negishi is a 2010 Nobel Laureate in Chemistry and a professor of chemistry at Purdue University. He was awarded the Nobel Prize for his work on palladium catalyzed coupling in organic synthesis, which is widely used as a technology that drastically accelerates organic synthesis reactivity. Palladium catalyzed cross-coupling led to breakthroughs in DNA sequencing, and practical applications of Professor Negishi's research include, among many others, the development of drugs to fight cancer and the manufacture of light-emitting diodes used to make ultra-thin TV and computer screens. Professor Negishi, please.
Much. Good afternoon. I am about to present my lecture, but I see a major challenge. That is that age-wise, level-wise, I think this is a very widest spreading audience that I have ever faced. But I'll try my best. Okay, so Mike? Yeah, sure. Yeah. Oh, by the way, in the title screen, which appeared before, it says, can you show the title? Transition, word transition has been mispositioned. So I want to fix that. So here it says, where is it? Huh? Oh, power of metal catalysis transition. I want you to place this transition over here. Transition, power of transition metal catalysis. Okay. Thank you. And that's what I want to talk about. And I'm glad to see a number of my serious colleagues, not just from here, but from Japan and other places. So I will attempt my story, to present my story. And but time factor is very, very important. Okay, so what is shown on the left-hand side? This is a chemistry that was recognized by the Nobel Foundation, which we came up with in 1976 or so. And here you see nickel, but we mostly use palladium because chemically palladium is more versatile, and palladium is a hell of a lot more expensive, but expense depends on how you view it. If this palladium catalyst, M, goes around and around and around, let's say 1 million times, even if it costs $1 million a mole, for producing 1 mole of the product, it is just $1, almost free. That's the power of this catalysis. Catalysis will make what cost $1 million just available at, for $1 per mole, right? For production of what you want. And as I was explaining earlier to younger people here, so this scheme will also show, what I conceived in when I was 26. So this is, in my mind, this represents the bulk of organic compounds. Carbon group, 2 carbon groups, R1 and R2, bonded with a C carbon-carbon bond, 2 carbon bond here. And to synthesize all kinds of organic compounds represented by this, I came up with a Lego game approach. I already told you. R1X, X is an electronegative element like this. Then R1 is plus with a hole. Mix this with R2M. M is a metal. And we have eventually screened many, but we have retained these, about 10 of them, 2, 4, 6, 8, 10 of them shown. And we kind of like zinc, scientifically, chemically, zinc is the most versatile, I still believe. You put one of these metals here, then R2 will be negatively polarized. So negative, so that means with 2 electrons, R2 with a 2 electron stick. And this stick, and R1 I said has a hole because X will grab the 2 electrons. With a hole, then if you snap it, then you can form what you want. All kinds of organic synthesis, organic compounds. So I thought, but there was one big barrier, between my hope and what can happen. And the barrier is that kinetics, in other words, energetics. So in principle, they should work. The Grignard reagents will do a fair number of those. But in reality, they often fail. And what was missing, we figured, was some kind of catalyst. So here, we ended up using nickel and palladium. Early on, in 1970s, in Kyoto, just saw Dr. Hayashi. That's not the reason why I mentioned this. In Kumada's group, Tamao and Hayashi and so on, they started using nickel. And that's the time I was looking for the catalysis. Then we too started using nickel, but we learned in a few years' time, there's a better one in the general sense, palladium. And to this day, in a periodic table, I think this appears to be the most helpful metal. Put palladium here, grab this R1X, and then it becomes this one becomes, okay. So anyway, it gets attached to metal, and then this X can be replaced with R2, like so. Then both of them are captured by this M. And then if M can release these two in the combined form, then this metal can go back so they can start going around and around and around. To this day, scientifically anyway, palladium, I believe, is the most widely applicable, and several other important advantages. Selectivity-wise, we can make organic compounds in a highly, highly selective way. And that's the main topic today. So I presented this for younger people, but now I'm going to have to quickly jack up and move up the ladder. Okay. So, well, this YES thing. Yes, yes. Obama. Yes, yes, yes. I learned from him. But I have never found the second Y. So it's a yes, yes. What is this? We have to achieve high yield. You put in 100 material, then you want to get 100 or nearly 100 products, what you want. So yield is important. Efficiency is equally or even more important. How many steps you need to go through. Later I will show some of my colleagues, very highly esteemed colleagues, they go through many steps. And using our palladium catalyzed methodology, we can cut the number into half or quarter, very efficient. So efficiency is a very, very important factor. And also selectivity. And I'd like to end up with some examples indicating exceedingly high selectivity for making a very delicate organic compound. How selective should we aim? How selective should these processes be? Well, as selective as needed, as selective as needed. And for making a very, very delicate so-called chiral handed molecules, we are claiming that we can, in most cases, not in all cases probably, in most cases we can jack up the selectivity to 6-9, 7-9, 8-9, and beyond. And my pharmaceutical colleagues say, well, if you go up to 7 nines, 99.99999% pure, even if there's a small amount of impurities, most of the time they may be okay. But I say, okay, if you want to jack up purity higher, we can do that. Anyway, that's where we have just reached last year. So, and of course, economy is related to yield and efficiency and selectivity. And another important thing is the safety. You talk about the thalidomide incident, and you know how important it is to deal with the safe chemistry. Okay, so with that, I have to rush. Okay, and my philosophy, a couple of my philosophies for doing organic synthesis. Well, of course, here in this corner, you have carbon, nitrogen, about 10 of them shown. Organic compounds mainly consist of these 10 or so elements. Obviously, carbon. I forgot, sorry, you should never forget this hydrogen here. It's separated, but. So 10 or dozen. But I felt we can bring in your synthesis all the other elements that can be usable elements, as long as you get the organic product. that was my proposition. Then, of course, there is 112 or 13 elements shown here in expanded periodic table. Then you realize all these technetium, polonium, beginning with 84 polonium, all these are red marked. Radioactive elements, 26 of them shown here. They are no-no in organic synthesis. Very difficult to deal with. So we avoid them. And then also red-framed one, beryllium. And all Japanese know how dangerous the cadmium is, Itai disease. All Japanese know how dangerous the mercury is, Minamata disease. So I advise that we stay away from. Professor Stille's tin, we also stay away from it. And so 7 of them shown. So if you take away, you're left with, of course, this green, yes, we know we need. Gray, not chemically very active, so it's hard to use, of course, except as a medium. All right, we're still left with blue. All these are metals. Blue metals, main group metals. Lithium, sodium, potassium, they are okay. Magnesium, in the Grignard reagent, we use, they're okay. So we get to use these blue ones. They tend to be relatively inexpensive. So we don't need, in many cases, we don't need to worry about their catalytic use. Then what else do we have? Having excluded all these things, smack in the middle, there's a 3 by 8 matrix. 24, 3 times 8, 24, right? 24, take away technetium, 23. These are the D block transition metals. And I have come to the conclusion that to the extent that we make good use of these 23 D block transition metals, I think we can protect our environment and we can benefit in many ways. So these are the ones that we should be using in a highly catalytic way. Okay, so that's a message for young people. And of course, we learn these elements from Mendeleev. So if you go to Moscow, then I urge you to go to this place, Mendeleev Institute. And you get to see this Mendeleev's periodic table. Almost 90 of them shown already century and a half ago. And I was also telling this yesterday somewhere. He discovered in a very scientific way 11 of them. Who else contributed new elements in the periodic table to the, introduced to our community? Madame Curie. Of course, she was a fantastic. She won 2 Nobel Prizes. But in number of elements she discovered. I should never say modest. She discovered 2. So, but what I'm trying to convey is that now, compared with most of us, 0, of course. I wish, really, we could have presented 11 Nobel Prizes to Mendeleev. How about that? In any case, we owe him a lot. And of course, he discovered in a very, very scientific way. He came up with a periodic table. And he saw holes here, holes there. And then there's a hole here. There should be an element. And if we discover this element, its density is such and such, and the reactivity is such and such. He predicted many of the things. When he did indeed discover some of them, there are actual experimentally observed behaviors right on, the agreeable, they agree with his predictions in most cases. So that's how I think we should do science, we should do chemistry, deal with chemistry, and I have my highest admiration. Okay, so these I have to skip. Getting back to this transition metal, cross-coupling, I'm sorry. Why do we need this expensive palladium as a catalyst? Well, without D-block transition metal catalyst, I checked when I was a graduate student at Penn, when I was 26. Well, these, organic compounds, they can be classified in terms of R1M and R2X. So they are same, but about 100 classes of organic compounds are represented by this scheme. Here, without catalyst, virtually nothing happened, nothing good happened. And when this carbon bearing X halogen or other X's are so-called alkyl, sp3 hybrid, alkyl, or acyl. In some cases, they work, fair number of cases, but they are not often, tend not to be very good. Okay, but after introducing palladium as a catalyst, look at this. All red 3 columns were now mostly green. Even here, halfway green. I think the rest of the area is becoming greener and greener thanks to younger scientists' investigation. Smack in the middle, 3 by 3, there is this no-no area. We tried to make this one acceptable synthetic tools, but without much success. In the meantime, we learned that just by shifting the point of carbon-carbon bond formation, in other words, make this side longer, one more longer, and this side shorter, like so, then we can have wonderful reactions, cross-coupling reactions. So we have solved this problem in this way. Okay. All right. And I was discussing, in Bangkok. So it seems like I just discussed this yesterday, so I won't discuss. I won't have to discuss this thing here. But basically, metals can provide low-lying, so-called low-lying, reachable, empty, open orbital. That's one good character feature of metal. This is what we take advantage of. For instance, here this is a hydrocarbon tetra substituted. So carbon, carbon, carbon. One hydrogen here, maybe. And the olefin, and mix them. Really, nothing happened. Nothing facile happened. But turned out that if you can manage to convert this thing into this 6 electrons, carbocation, then fast reaction takes place, and you form this carbon-carbon bond. Okay, we accept that. Then Professor Brown, my lifelong mentor, Professor Brown's hydroboration. He discovered this hydroboration, and he won his Nobel Prize in 1979. Why is hydroboration or many other hydrometallation reactions so fast, so facile? So by going from this to this, we can speed up the reaction. And if you compare this carbocation structure with this metal boron hydride structure, we call this isoelectronic. You see this part, this part, this part, this part, this part, this, all the same. Isoelectron. No wonder hydroboration works so fast, and then we can get this hydroborated product. Well, is it limited to Professor Brown's boron? Turned out no. Well, later, hydrozirconation was similarly discovered and developed, and many other metals, as you can see. So you can sense that. So these are the fundamentally important scientifically fundamentally important things in chemistry. Well, sorry, I don't have time to go through this one. And another important thing that Fukui and Hoffman, so here, Fukui and Hoffman, well, Woodward did not, well, maybe we should include Woodward. But actually, what I'm showing here was reported in 1952 or so by MJS Dewar. 1950. Anyway, but that's right. But this scheme is called, shows the significance of electron, this empty orbital, this white one, this butterfly-shaped one, does not contain electron. Empty orbitals, Fukui named this one LUMO, lowest unoccupied molecular orbital. Those were, before Fukui and Dewar, they were not even considered seriously. But they emphasized the significance of this LUMO. And to make a long story short, which this was the chemistry I was discussing in some detail in Bangkok. But in facile, very fast reaction, what is needed is, okay, so dark ones have 2 electrons. So 2 electrons inside, the 2 electrons go up into the, flow into this empty orbital, white one. But that's not it enough, that's what they say. So here, butterfly-shaped dark one with the 2 electrons, they can be transferred from top to bottom. In other words, two-way street. In a countryside, a one-way street, the car comes here and the car comes from there. They bump each other. It's very difficult. But if you have a two-way highway, then one goes this way and the other one goes this way. Well, it's not the same, but as an image, you can think of that, this catalysis or reaction like this. And this is an extremely important concept. And if you accept this 2 electron up, 2 electron down, synergistic bonding scheme, now you apply this to Professor Brown's hydroboration of olefin. Okay, so you can write this scheme, kind of similar to this one. Inside, the same, 2 electrons go up. Outside, boron hydride with 2 electrons down, you see. So this is an up and down motion. That's why, this is the reason why hydroboration is very, very fast, very facile reaction, and very selective, okay? Now, if you accept that, then I thought, well, I did not invent this reaction, but in fact, we discovered a fair number of carbon-metallation reactions represented by this one. Carbometallation, because carbon and a metal bond add to pi bond. Hydrometallation, because hydrogen and metal. So I said, if hydrogen and the metal does this is a very simplistic notion, but it works very well and the powerful principle. If we replace hydrogen with carbon, shouldn't they also do this? This is how we discovered many carbo-metallation reactions for olefins and acetylene. So just recognizing this from Fukui and Hoffman duo, and then replace this hydrogen with carbon, and then now we have a all kinds of carbo-metallation, carbo-zirconation, and so on and so forth. Okay. So chemistry is very interesting. You can be very, very creative in this way. Okay. But then I thought, we shouldn't stop here. What else can we place here? I say anything in the periodic table, 90, 100, I don't know. Many doesn't know. So, for instance, you can put a halogen here. Then you can have a halo-metallation reaction. Okay, if you are if you have learned the foundation of chemistry, then you might say, if you put a halogen here and the metal here, then that's an energetically very strong bond. Cleaving that and adding to olefin, wouldn't that be a contra-thermodynamic? So reaction, uphill reaction. If you thought that way, you are excellent. In fact, in most cases, it is a contra-thermodynamic process, which is a big no-no, big no-no. However, you should never say never. If this metal is very non-metallic, not very highly positive, such as when you think of a metal that is not highly metallic, boron. Boron is a pretty electronegative metal. So halogen and the boron, haloboration reaction is no longer contra-thermodynamic. It is thermodynamically downhill. Then you're okay as long as kinetic barrier can be overcome. And in fact, Mike Lappert in UK already discovered this haloboration reaction. And as you can see, all these reactions are sticky addition reactions. What this means is that their addition is, as shown here, H and metal, C and metal, so on. They're almost 100% syn addition, almost very highly selective. So that's how we have explored all these areas, and we're still enjoying. Okay, but let me see. I'm going to have to hurry. So this one I'm going to skip. And here I am crediting those who developed palladium catalyzed cross-coupling. Here, Murahashi, Ishikawa, Forbark, following the magnesium nickel version of Tamao, and Kumada, and Koryu, and now Dr. Hayashi. Also should be in here. And then we did this in mid-1970s. And then a few years later, we learned that some other people also were interested in, which is okay. Anyway, and we can now, with this cross-coupling methodology, we can make all kinds of various kinds, I should say, complex molecules like this in a very highly selective way. But I'm going to have to skip this part, and I want you to just glance through this. And before our time, synthesis of some of these kinds of compounds were exceedingly difficult, time-consuming, and so on. But now, many of them have become readily accessible. For instance, if you put 3 double bonds side by side, okay, then each one can be trans, as shown here, or cis, as shown here. There are 8 of them, 2 cis-trans, 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 2 by 2 by 2, 2 times 2 times 2, 8 isomers, stereoisomers possible. 4 of them are shown here. And so these were barely synthesized before us, but that's not in a very efficient way. And recently we said, okay, let's just make them all. And we made them all. So 1, 2, 3, 4, they're all different, all in acceptably pure form and in excellent yield. Okay, so that didn't surprise us. But nobody had ever synthesized the remaining 3 shown here, and I think 1 more, 2 shown here, and 2 more coming up. With this middle, anyway, the cis bond here and here and here. But using the palladium catalyzed cross-coupling, there's no problem. So once again, stereochemistry very high, yields are excellent. The final 2, some of my group members came to me. We cannot make them. We cannot synthesize them pure. Well, we've already made 6 of them. Why do you think that we cannot make them? Well, nobody else has ever done this one, and I don't think we can do that. Okay, anyway, let's do it. We did it, and no problem. Okay, so here cis double bond and cis double bond, cis, cis, cis. Okay, still better than 98% selective and excellent yield. So we ended up publishing this one a few years ago, as shown there. But now, so this one is a CoQ10. Kaneka is making this one, but we reported this thing a while ago. And once you make these small pieces, then we can synthesize them in 8, 9 steps. And I got a phone call 20 years ago when I got results. They considered, but they decided to continue their fermentation method, which they use. Now I got another phone call recently, so I'm going to have to visit them. I think they want to do it, switch to chemical approach if they judge that it is more competitive. So so as you can see, we form all these 20 or so carbon-carbon bond in a hurry. Okay, but what I wanted to really tell you, okay, I don't see any hands, so I will continue a little bit more. There are a whole slew, I wouldn't say millions of them, I haven't seen millions of them, but thousands and thousands of them. And you see a branching here like this, and you don't see double bond. So all these are so-called chiral, they have a chiral center. And these things have been troubling synthetic organic chemists ever since Pasteur saw the right-handed molecule and left-handed molecules under the microscope. And then with the tweezer, he separated left here and the right here. So he got optically active tartaric acid, both right-handed and left-handed. Well, it is acquisition of isomerically pure optically active compounds, all right, but no synthesis, just a tweezer. No? So arguably, this is one of the last bastion to conquer. And we started challenging this, and as you know, Pasteur came, and not a Grenier, but Emil Fischer. Emil Fischer won the 2002 Nobel Prize, the second year. He was able to make all kinds of chiral compounds, sugar, but never in a catalytic way. Okay, we have to make them catalytically. Otherwise, economics are against us so much that probably they won't be very useful. And to make a long story short, we came up with this new reaction. So here, new chemistry will lead to new, developments. And obviously, I don't have much time to discuss. So we call this reaction. I just want you to remember this name, ZACA, Z-A-C-A. ZACA reaction. We needed to discover this one, and which we did. So one is a genius, a Russian from St. Petersburg, but he was preceded by a Dutch boy, American boy. But anyway, so in 1995, 17 long years of struggle, we finally discovered this reaction. So simple terminal olefin here. Now we add R2 and aluminum in this way. Aluminum goes to the terminal position, R2 in this position. And here, as you can see, R2 may approach this carbon from your side, front side, then you get this one. But R2 may equally, with equal facility, approach from the back side, then you have to draw this one broken line. Then it's a racemic mixture, useless, okay? So we must ask this R2 of this aluminum to approach only from the front side, not from the back side. To control that, we needed to use this reagent, which actually came from Gerhard Erker. But they were only doing this polymerization reaction. So we call this a ZACA reaction. I want you to remember this. We are very, very proud of this reaction. With this, to make a long story short, well, actually, why did we need it 17 long years? Well, we knew that what we needed to do, that is to start with this terminal alkene and add the methyl or carbon and aluminum and the zirconium, some kind of catalyst, and to go from here to here, right, as I told you. But most of the reactions that we carried out would go further in this way or this way, and so on. So there are many no-no territories, and we needed to avoid this no-no territory to stay here. Well, genius guy, Denis Kondakov from St. Petersburg did it. 1995. Okay, once you get this, then you can do all kinds of good things as shown here. Okay, I don't explain this one. And here in this business, statistical amplification and some other factors are important. Here, statistical amplification. If there are more than one chiral center in your target molecule, then purity or enantiomeric excess is a term. Stereochemical purity goes up statistically. In other words, if you have one such center, and suppose this is 80% EE. 80% EE means 90 to 10 mixture. 90 minus 10 is 80. That's why we call this 80% enantiomeric excess. But if you can afford putting 2, then the same kind of reaction of same selectivity level will give you 98% E. Jump up. If you can afford putting 5 of them together, then this enantiomeric excess purity goes up to 99.9997. Okay, so this is a very, very important principle and a general, mathematical. This is a mathematical principle. So in any case, one thing we like to do is to start with allylic alcohol. Allyl alcohol, double bond here, no methyl, no iodine, allyl alcohol. And then you add methyl and aluminum. Aluminum is replaced with iodine. This is a very, very useful intermediate, small compound that we use. Okay? So once we get this, then iodine can be replaced with all kinds of double bonds or aryl or alkynyl or benzyl, you name it. So you can have all kinds of chiral compounds with asymmetric center here, in this position. Okay. I show you one cute little synthesis example. So this compound is called the acid component of praying gland wax of gray lag goose answer. All members of my group, research group, must be able to say in one stretch without looking at it. Okay. Anyway, so this is grease, the wax that geese, Siberian geese, have in this part of. They have to fly 1,000 miles over the Japan Channel or whatever they call. So it must be a super grease. Our synthesis is the second one. And Kenji Mori, my friend at the University of Tokyo, synthesized this more than 20 years before us. But their synthesis required 20 steps, overall yield 1%. You cannot make a business. You cannot go into the business with that. Sorry, Kenji Mori. But I'm showing here 10-step synthesis, overall yield 12% or something like that. Numbers will show. Okay, first we start with allyl alcohol, carry out this Zaka reaction. In other words, methyl here, aluminum is replaced with iodine. Okay, Zaka. And then cross-coupling. We replace this one with double bond. 2, 3, 4, 5. Zaka vinylation. Okay. So last one is Zaka oxidation. So after 1, 2, 3, 4, 5, fifth step, we get this one. Now it begins to look like this one. Huh? Okay, but if you examine this one, we learn that it's a 9 to 1 to 1 to 1 to 1 mixture, stereoisomeric mixture here. Okay, and then we found this yellow box. As long as we have this yellow box, that yellow box can be readily purified. These are the tricks that you have to find here and there, and you have to be lucky. So with this OH in proximity, this diet, 2 methyl groups hanging, can be readily purified. So now chromatography. So half of the molecule, nearly half of the molecule is pure. Okay, then what do we do? Well, we so we modify this part, and the methyl, so OH is replaced with this thing. And then we deprotect. Now you see yet another yellow box. 2,4-dimethyl 1-hydroxybutyl. This is the same except for the chirality. So now this can be readily purified. Then the whole thing is now pure. In other words, oops, this center, this center, this center, this center, all pure. Then we just oxidize twice, and then you get this. 10 steps, 12% yield. Maybe someone can think of, if this is a super hyper grease, make and sell. And you can see, of course, it is very, very pure. Okay, I have to rush. Something like that, you can readily synthesize, but I skipped this one. And another important thing is so-called Charlie Shee's selectivity factor, E. So if the selectivity factor is very high, and then you can purify many of such compounds readily. If it's very low, then it's very difficult to purify. So we call this E factor. And E factor of 33, 40, these are pretty high, easy to purify. But these similar. So chemicals are asked to distinguish this methyl with ethyl. Chemicals are confused. Yeah. Okay. So okay. So anyway, so now we can synthesize all kinds of chiral compounds pure using these. There is this paradigm shift thing, the plan. So let me just explain, and this may be the last one. You start with a simple aryl alcohol, Zaka reaction iodinolysis, you are here. Okay? If you use plus Zaka, you get this one. If you use minus Zaka, you get this broken line here. You see that? Okay. They are both 80-90% E, not very pure. Not pure. But you can use Chue-1 and other, amano company, lipase. So now we bring a biochemical lipase, then you can readily jack up the purity over 99% E. So very quickly we can get this very pure one, very pure one. Now time for cross-coupling. So palladium or copper sometimes is also good. You have to choose one or the other. And you can readily replace this iodine with R2. Then you get a pure one. But these turn out to be an easy one for us to synthesize because this asymmetric center is only alpha, beta. On the second carbon. But question is, if this center is away from this OH, then what happens? It gets much more difficult. Or if these two groups are very, very similar like this one, many people struggle to make a pure compound of this one, which they wanted to use as a starting compound in many natural product synthesis. But now we can make this thing pure very easily. And not only that, look at this thing. Yeah, okay, so sorry. Methyl here and the CH2D. So this is isotopomer. Difference is just by one isomer, hydrogen or deuterium here. And no problem, you can make them. So let me go, and even something like this, isotopomer, okay? Here CH2, CH3. So this side CH2CD3. Chromatography is very difficult to distinguish, but now we make them pure. And of course, we can detect them as pure, isomerically pure compound. So like this one, and last, resort for analysis is not the chromatography, but NMR. Turned out to be NMR. So this is a good one, but I don't have time. So let's just go all the way. And yeah, here. Okay, this is the last slide. Alpha, beta, gamma, delta, epsilon. Very remote, So it's very difficult. And this one is not isotopomer, but ethyl here and a propyl here. Here we couldn't analyze chromatography or separate chromatography. NMR is about the only tool that survived. We started using Moja-Ester, but in this case, Moja-Ester analysis was not good enough. Boy, we ran out of NMR as a tool. So we thought, and then my group member found that at the Tokyo Institute of Technology, there's a group which modified this Moja-Ester phenyl group here, CF3, naphthyl, and the methyl. This one is far-reaching, and you can tell the difference between R and S in a remote place like this one, RR plus RS. See, triplets are all split into two. But if we make them pure, single isomer, then we see this one but not this, this but not this, this but not this. So we know that this is very, very pure, very, very pure, enantiomerically pure compounds in a remote place. And chromatography, no. NMR, Moja-Ester, no. But this MNP derivatives, yes. So this is the final story, I'm sorry. And these people have participated in cross-coupling, and then a more recent work Purdue gave me this gift this year. Well, as you can see, people from one gigantic country is dominating my group. And here again, thank you very much.
Thank you, Professor Negishi. So for the next 30 minutes, we will open the floor up for questions. And you can please feel free to use the standing mics located along the aisle in the auditorium. Or if you're very inaccessible, we can try and get the mics to you. Question? I think they might be turning it on.
Okay. Hi, Professor. How are you today? I'm a third-year chemistry student from Penn. Yeah, and I've seen your face downstairs in the chemistry building for the past 3 years. Can you hear me now? Yeah, I can hear you. Okay. Hi. I'm Lillian. I'm a third-year chemistry student at Penn. Yeah. I've seen your face downstairs for the past 3 years in the chemistry pit.
Are you asking if I was, or I told you that
Yeah, I know.
I may still have a school record in obtaining 8 straight excellent means 80% or more in so-called cumulative examination. In one case, I was the only one above 80.
Well, Well, I'm not going to ask you a technical question, but what kind of advice do you have for young people just trying to figure out what they want to do in their next step in life?
Try to develop what?
Or trying to figure out what their next step in life is, you know?
Sorry, tell me again. Last part. It's okay. Sorry, I failed to understand the last part. Please tell me again.
Okay. What kind of advice do you have for young people trying to figure out what their next step or steps in life are going to be, you know?
Well, I was telling perhaps this morning somewhere, and I say, you know, everybody goes through elementary school, junior high. There, I think you have to be among really the tops without straining yourself, cramming yourself. And then high school. High school is a real challenge, and because I'm sure universities here entrance examination is pretty tough, and so that's the time when you want to pick a good university and to be able to get in. So really fundamental intelligence, intellectual capability should be elevated. I was emphasizing the significance of high school math and high school chemistry and so on. And they are the foundation of our activities, research activities for the rest of our lives still. So do well in high school and in college. And then if you graduate from top university, and I say you are already 1 in 1,000 kind of intellect, 1 in 1,000. So what should you be? 1 in 10 million. Eventually, you want to be 1 in 10 million. You know? So that is what I call a 3-step cleared, 4 more steps remaining. Okay? And when I won a Fulbright scholarship, that was about 1 in 100. But anyway, I went to Penn, and I received a fantastic graduate teaching. And I got a PhD degree in 3 years. And looking back at that time, I was a 1 in 10,000? 1 in 10,000 kind of individual. Is there any justification for my saying that? Well, US-Japan Fulbright program sent about several thousand Fulbrighters to America. I'm not talking about travel money only, all expense Fulbright, several thousand. So, and of the several thousand, several of us won the Nobel Prize, including myself, Tonegawa, Professor Tonegawa, and Shimomura, and I forgot, anyway, 4 or 5. So for several out of several thousand grantees, that's 1 in 1,000, right? So looking back, I consider that to be our 4th step. The 5th step, my postdoctoral study in Professor Brown's group. Any justification? Professor Brown has had a couple of hundred PhD students and postdocs, including himself. 3 of us won the Nobel Prize. Brown, myself, Akira Suzuki. So 1 in 100, right? And so I consider that to be a fifth step. And people ask, what is your sixth step and seventh step? Because 1 in 10 million means 10 times, 10 times, 10 times, 10 times, 10 times, 10 times 10. Okay? So I say, oh, come on. You take care of the last two steps, sixth and seventh step. That's your responsibility. But it took me 35 years to get a Nobel Prize. Climbing up sixth step and seventh step. But this is, of course, an image story, image story. But I hope you understand the process of reaching that. And I think there is a route. Don't buy lottery, don't treat this like buying a lottery ticket. You only lose money. You never win. Okay?
Any more questions?
Hi, good afternoon, Professor. Thank you very much for your talk.
Well, thank you, thank you.
A lot of your talk is about your personal experiences in making discoveries and so on. So actually, from hearing from your talk and also hearing from friends who did chemistry and stuff like that, I understand that the work of chemist is actually quite tedious. Actually, you have to work very hard to actually perform experiments, and actually, when you look at the results, you need to have a sharp eye to be able to identify what possibilities might go beyond the experiment, and that's how you move on to your next steps and so on, right? So you also described your Zaka reaction where I think you mentioned it took around 17 years to reach that step, so it actually takes a very long time. Now I've actually been thinking because I mainly work in an area more related to electronic design, automation and things like that. So maybe taking reference from the electronics industry when new circuits are being designed and things like that, there's actually a lot of tools out there that help to speed up the design process and assist electrical engineers and computer engineers to actually devise more better designs from what they already have. So actually I was thinking, do you have any opinions on how chemists could actually, whether there can be any possibilities for tools to come out that could help chemists to be faster at making discoveries and be better at what they do?
Mm-hmm. Well, my simple answer to your question is that tools can be a very valuable, useful tools, but tools don't discover. So our mind will lead to the discovery. So I think we need both. But of the two, I consider the latter to be far more important. We use a lot of tools without some of the finest tools, the NMR in particular, I was explaining towards the end. We couldn't have done this kind of work. And I was asked by my group members, please buy this kind of chromatographic instrument and that kind of chromatographic instrument. Wait a minute, didn't we buy that? Well, that was not enough. That's not enough anymore. We need to buy this. And I bought another, advanced instrument. And eventually I said, well, maybe we ran out of the chromatographic tools in our research. And then we went to NMR, or more the older tool. And that came in rescue. But even that, as I was telling you, we needed to select good reagents to use together with the instrument. So I still think that in these kinds of scientific endeavor, what is by far the most important is what you think, what you come up with in your head. So in my case, as I was telling you, this Lego game, the analogy between the organic synthesis and the Lego game. In fact, looking back, that was a very useful thinking for me. And I would like to think that science and engineering, to considerable extent, will remain as fields where our brain, our thinking, will play the most significant role. In my research, definitely, and if I may say so, I hope I won't get bitterly criticized by my current and former associates. I needed to come up with some basic things myself, many cases. And I am very proud of that. I wish that the younger people can beat me in this respect, but I am still competing with my group members. And I think I'm winning. Okay.
Hello. Yeah, thank you, Professor. Sorry.
Thank you.
Following on from this question, it's a sort of a question of from your experience of making a discovery. So usually, I guess it's kind of also about life. Like when you sort of make your way to a certain point, and when you look back retrospectively, things you can kind of trace the dots and see what led you there. But have you ever had an experience of when you made a discovery and you felt you made one big round and actually things would have been much faster if you had done made another choice or took another step that was different from what you had taken? Maybe you could share an example of such a thing then.
Well, I'm not sure if I fully understood what you said, but thank you for your comment.
Do you want to rephrase your question?
Yeah, sorry, I guess I'll rephrase my question. Have you ever had after making a discovery, and when you look back at the progress to the point where you made your discovery, do you ever have do you have any thoughts of you could have you have made your discovery in a shorter time had you made a different choice back then in time?
Different choice of what? Instrument?
I guess it's quite a general question. I mean, whether you had, it's quite a general question, whether you have any sort of experience from your own.
No, I am, on one hand, I'm very pleased that we have made a series of discoveries and subsequent developments. On the other hand, I often wonder, why did we spend so much time to come up with a final discovery? Shouldn't we have done sooner? But having accomplished some of those, I'm happy. Yeah, I think that's the reality and the real life situation.
Thank you, Professor.
Yeah, thank you.
It doesn't have to be scientific, so you can ask him any questions, including questions about the periodic table. I'm sure you memorized it, Professor. Now I'm asking them to ask questions, so just a quick question anyway. So are you still taking in grad students?
Pardon?
Are you still taking in grad students?
Oh, yeah. Of course, yeah. I'm here.
Yeah, so if any
I
of
came
you are
here
considering
to accept an entertaining question, right? No more.
It is about the periodic table, actually. There is a trend recently to move away from palladium catalysis for some transformations because of, you mentioned earlier on your talk about green chemistry, but because of sustainable chemistry and limited resource when it comes to palladium. But moving away from that for more abundant metals such as iron, we do sort of create other problems in terms of purification and the amount of material you have to use. I'd just be interested to hear if you have a comment about the balance between those in moving forward in the manufacturing industry, for example.
Balance between?
Between using something like iron, for example, for certain transformations, to replace palladium from a manufacturing point of view.
Iron is cheaper, you're saying?
Yeah.
Okay, well, it all depends on the overall factors. You know, I am never, but in the end, I think YES, yield, efficiency, selectivity, safety, and economy, you know, those things must rule. And you are saying that use of cheap metal elements like iron and so on, they may come out ahead of let's say palladium, expensive palladium. If that is, in an overall sense, if that's the case, we use iron anymore. You know. But remember, in catalysis, the turnover number, and many other things, but among others, turnover number is very, very important. Yeah. If 1 mole of palladium turns over 1 million times, which it tends to do, and iron turns over much less, much fewer time, then the cost differential may be even upset. And there is also a selectivity issue. You know, if you get a mixture of the products, you're going to have to purify. If you don't get a poor mixture, which can be readily cleaned, then that can be less expensive. So this is an overall thing. And in many cases, we find palladium catalyzed reactions are cleaner, higher yielding, and very highly turning over catalytic reaction. And well, it's our choice quite often. But we are not married to palladium. So if we find copper to be superior or even nickel to be superior, we don't mind using. We will use it. But boy, palladium in the cross-coupling area, I believe is best choice in many, many, many cases, scientifically. Yeah.
Okay. We will encourage actually the students to ask questions, especially from that side. It seems pretty quiet. Oh yeah, go ahead.
Hello, Prof. I would like to ask a question. What is your current research interest?
Pardon?
Basically, what is you and your team is currently doing?
Sorry, I failed to. What is what?
What is your current research interest?
Current.
Current research on like what kind?
I couldn't understand that last word.
What kind of research that you are currently working on?
Huh? Oh, current research interest.
Yeah.
Well, so only last year, we have finally reached the pinnacle, the top level in asymmetric synthesis. And we feel that we can now synthesize a wide variety of chiral compounds, as pure as you want, as I have been telling. And to my knowledge, sorry, there is my respectful colleagues, Hayashi and others, Kobayashi. But we feel that we have finally reached the pinnacle level, and where we can be very, very proud of. And then I think they are also serviceable, in other words, commercially attractive. So then now you ask me, what's next? Good question. What are we doing now? I think we are busy right now. Right now we are busy polishing up, just refining the overall work, our overall work in asymmetric synthesis area. But I have to think about next one. Thank you. I will do that.
Thank you.
Thank you very much for your talk. In the beginning, you referred to the frontier molecular orbital theory and how it helped you to discover new reactions. So how would you evaluate the importance of theoretical and physical chemistry in organic synthesis research?
Very, very, very important. After all, I also say the same. High school, for instance, high school math. High school math we use all the time. For instance, if one-step reaction is a 90 yield a 90-10 mixture, if you get to go through two steps, then it's a 90 plus 10, 90x plus 10y square. Then you open it, and the first term, the last term corresponds to the enantiomeric term, because all the middle terms correspond to diastereomeric terms. And then enantiomeric excess will significantly improve. And if you go through third one and the fourth one and the fifth one, then really enantiomeric excess goes up. I think this is a nature's trick. You can see amino acids. Amino acids are linked together. They're all chiral, most of them, except for the simplest one. So, and then maybe 100 of them may be linked. At which point, that 100 mole or so is enantiomerically very, very, very pure, if you can separate wrong isomers, okay? And maybe nature has a way of easily separating. And then you digest the peptide, and then you go again. No wonder our amino acids and so on are so ultra, ultra pure. This is a nature, mathematically dictated nature's trick, because they polymerize to pure one, and then digest to pure isomer, of course, after separation, after some weeding out. And then they do again, over and over and over again. So people wonder why biomolecules like amino acids and so on are so highly pure. And of course, there is a mathematical reason for that. So we take advantage of those simple things.
Thank you very much.
Yeah, thank you.
Hi, me and my friend are students. We are students from the Japanese school, secondary school. Is it okay if my friend asks you a question in Japanese?
Yes. Maybe I understand better.
お話ありがとうございました。
But you have to wear a mask. Sorry.
お話ありがとうございました。
はい、どうも。
なぜこの仕事に就こうと思ったんですか？
はい。なぜ？
なぜこのような仕 事に就こうと思ったんですか？
フィールドっていうか分野のこと？はいはいはいいろいろ迷いましたよ、私もね。Maybe I should answer your question in English. So, okay. So she's asking why I chose my profession, my career. Well, of course, I can never say that I have dictated. You know, I have dictated all my course as I have done. But okay, maybe I told this morning. When I was a college student and high school age, I was so determined to major electrical engineering. I thought that was really cool. And then I went to college, and almost every day I was with a senior person. We are going together. And he started saying, he's a couple of years older. And he finally joined the Hitachi. You may know the name. Hitachi company. And he said, oh, Hitachi is such a stingy company. For that matter, most of the electronic industrial companies are stingy. Low paying. And I said, oh. I was thinking of eventually getting married with my wife. Now, this, I have to think about this. But at the same time, it was a time when, especially in Japan, but worldwide, polymer industry was booming. And when I learned about that, Ziegler, Natta polymerization, and so on, DuPont, nylon, Tetron, Dacron, and so on, I was fascinated by this polymer chemistry. So between two of these, I simply switched to polymer chemistry. So I joined the Teijin Polymer Company. And looking back, I don't know, maybe in my heart, I liked electrical engineering better. But polymer chemistry, not bad, looking back, because that is more closely related to what I subsequently did to win a Nobel Prize. Not bad. Thank you.
I would like to ask this question in English, although I can speak Japanese. I'm in 9th grade and I've been studying hard for my...
9th grade?
9th grade.
Now?
Now.
Oh, you look like a 12, 13. Anyway, okay, wonderful.
And I'm studying hard for my high school exams. And I don't know, although I'm studying hard, I don't know if I have a bright future, Bright future in one more time, tell me. I don't know if I have a great life in the future.
Oh, you are concerned about your own capacity.
So I want to ask you a simple question.
Yeah.
If you study hard, will you have a great life?
That's a very good question. In other words, I won't be able to answer. Okay, but I can look back my case. So as an elementary school kid, junior high school kid, I never studied outside the classroom. But I was always a top student, and and sometimes 100-point full mark all year long, you know. I didn't know. I wasn't even aware of that, but my mother went to school, you know, for Parents' Day. she would come back and would tell me, oh, I didn't know that. Anyway, then I went to more competitive high school. Then maybe I was telling you, I told you already. After first year, my report card said 1, 2, 3. 1, 2, 3. I still remember 1, 2, 3. What is this 1, 2, 3? I found out my ranking was 123rd out of 405 students in the entire class. At that time, my high school, which is a pretty good high school, was managing to send about 40, including one year, how do you call, anyway, 40 people annually to University of Tokyo. But 123, give me a break, I cannot make it. And then a while later, I realized, well, but 120, but I never studied in the first year. So if I studied, what might happen, you know? So all of a sudden, I began studying hard. Half a year later, I found my ranking was 9th. Ooh, 123 to 9th? That's nice. And 9th is well within the 40 or so that school was sending to the University of Tokyo. And following year onward, I was always number 1. Sorry to bragging about. But my point is that you have to be good. You have to be good at this point, at this level, to go. So I consider high school, college level, 3rd step in the 7-step climb to Nobel. Okay? So to be able to climb up, you have to be fundamentally good. And I felt, looking back, I was very good. Sorry to brag about it. And then I applied for the Fulbright scholarship, right? And I won it, my first try. 1 in 100 success ratio. And then on this program, about several thousand Japanese went to America. Tonegawa, Shimomura, myself, I forgot a few others. So several out of several thousand. So already 1 in 1,000 from the top. So that is from the other side, what is that, 10,000? And then I came to Purdue as a postdoc. As I told you, about 300 people associated with Professor Brown, where I cheat here a little bit, including Professor Brown himself, Suzuki, Akira Suzuki, and myself. 3 of us emerged as Nobel Prize winners out of overall 300 or so groups. Well, he had 20-some people at one time, but overall 300. So, that makes sense. And as I may have already told you, 6th and 7th step, people ask, 6th and 7th step, how do you climb up the last final 2 steps? You do it on your own, which I did. but it took me 35 years before finally I won a Nobel Prize. So I think what I'm saying is that one has to evaluate your raw material here. And it should be good in one area that you want to pursue. But maybe you may not be good in this area. If you start trying along this line, and a few years later, if you judge that that's not really the area that I want, switch to another one. I was telling someone about this concept of repêchage in rowing. One loss, you are not out. You can come back and you can try, then you may actually win. So there are some of these kinds of positive thinking that one should have. That's how I think.
Thank you very much.
So, thank you for the questions. Ladies and gentlemen, this marks the end of today's program. So please join me in thanking Professor Negishi once again.
Oh, yeah. Thank you very much.
We would also like to thank His Excellency Mr. Haruhisa Takeguchi, Mr. Uwe Morawetz, Mrs. Negishi, and Professor Andy Ho. Last but not least, thank you to all of you for attending the event, and have a good afternoon.
Thank you. Hmm? Yeah, no problem.